Yeah, that's good. Yeah, good point. So yeah, as I was saying, we are going to do the thermodynamics and the conservation principles today. And let's start with the thermodynamics. Essentially, propulsion and the analysis, the fluid mechanics and heat transfer analysis of propulsion, or the chemical reaction parts of the propulsion, is essentially the analysis of a duct flow, right? Because we have a flow inside a duct, right? That's it. It sounds pretty simple, but it is very complex, right? There are different parts of a duct flow that are of interest to us. The friction that is going to happen between the walls, between the your air or whatever you have in that specific duct, and the blades of the turbine compressor and all of those things. The other important part is the chemical reaction that is happening within the duct, right? You have a combustor that's essentially exploding the air, if you will. And the variation inside the area of the duct is very important in the fluid mechanics analysis or aerodynamic analysis of the propulsion. And the compressibility is of an immense importance here. We are going to also see the appearance of shock waves. So the compressibility part is very important. You have to keep in mind that we are not dealing with incompressible flows here. We are only going to deal with compressible flows here. And also, if we move to the supersonic conditions or transonic conditions, you are going to see the appearance of shock waves. Who in this class is not familiar with shock waves? We will talk about them, but we're not going to into that much detail. So all of you, okay, that's good. Just very simple review of thermodynamics. The medium we are dealing with here is a perfect gas, mostly air, right? Air comes into your propulsion device and goes up, right? That's mostly. This is not true for outer space travel, but we don't deal with the outer space travel here, right? We talked a little bit about it in the orbital mechanics class. I think that some of you have taken already, and that doesn't really discuss the propulsion devices, if you will. So we are only dealing with air, mostly air. Mostly air. So the main assumptions we are making here is that the intermolecular forces between the molecules are very, very small, and the volume of the molecules that occupy space is also very, very small and can be ignored. These are the main assumptions of a perfect gas, right? Essentially, the collision between molecules is non-existent, and the molecular volume is also essentially zero. So, using these assumptions, you can come to the equation of state for the perfect gas, which is P equals to rho RT. Rho is the gas constant. Right? I'm pretty sure you are all familiar with this, hopefully. If not, then we are in a lot of trouble. And you can calculate the gas constant for each gas by using the universal gas constant, or bar, divided by the molecular mass and the weight of the air, of whatever gas you're using. The universal gas constant is 8,314 joules per kilomoles Kelvin, or we can also have it in the imperial units, British units. That is very popular here. Any questions so far? Very simple. I'm pretty sure you guys are very familiar with this. We can also define the specific enthalpy and energy of the system using these two formulas. Essentially, we are saying that the enthalpy and energy of the system is a function of heat capacity at constant pressure and constant volume, and the changes in temperature. The heat capacity at constant pressure and constant volume itself is assumed to be a function of temperature. If they are a function of temperature, we call that gas a thermally perfect gas. Okay, and there are a range of temperatures in which we can assume Cp and Cv are constant, don't change with temperature essentially. And those gases, or those ranges of temperatures of those gases, in those ranges of temperatures, those gases are called the calorically perfect gas, where Cp, heat capacity, constant pressure, heat capacity, constant volume, are constant and don't change with temperature. Any questions here? Okay. Okay. So the next part of thermodynamics, which is one of the most important parts of thermodynamics, is the first law. The first law of thermodynamics is essentially relates the heat input or output on the heat input in the system or output out of the system to the changes in energy of the system and the work done on the system or work done by the system and environment on the surrounding environment. You just have to keep in mind that delta beside Q and W refers to the fact that it is an elemental change. We are talking about an elemental change in Q and W, in heat and work. And D here, DE, just beside the energy, is a differential change. So what does it mean? It means that Q and W are path dependent. Okay? So heat and work are path dependent, whereas the energy, the changes in energy is not path dependent. It just depends on your energy state at the second level, your energy state at the first level. Okay? So you can essentially take the integral of energy and find the you can find the changes in energy using the energy state of the first level and the second level. But you can't do that with heat, right? You have to know the path that is your heat has gone to get from 1 to 2. Does that make sense? Okay. So, as you know, is there any questions here? No? Okay. As you know, we deal with cycles, right? We deal with cycles and cycles. The Brighton cycle we dealt with is essentially it is not a good word to use for it. It is not an open cycle, but the exhaust doesn't go into the inlets of the propulsion system, right? So we can say it is an open cycle. But thermodynamically, it is still a cycle. It means that it is closed. It is a closed loop. And I can essentially say that the changes of heat within the system is going to be equal to the changes of work, the elemental changes of work in the system, right? Any questions here? So essentially, changes of energy in a perfect system is going to be 0, right? Internal energy. And I know we have had, how many submissions have we had for the bonus question? I know we have had 1, 2, 3. Okay. Yeah. So we have had some submissions for the bonus questions. That actually, this is the principle you have to use the same as we did to improve the efficiency of for the bonus question, right? This is one of the principles you have to use. Any questions so far as the first law and its relationship to the cycles go? No? Okay. So second law of thermodynamics, of course, you know that in the second law of thermodynamics we introduce entropy, this new variable, very important variable in thermodynamics, and in thermofluid systems design and analysis. We can define the second law of thermodynamics using the Clausius inequality, TDS. temperature of the system multiplied by the changes in entropy is always greater than the heat, that elemental changes of heat, or greater than or equal to the elemental changes of heat. But what is the case? What is the case of equality instead of inequality, right? What is the condition where TdS is going to be equal to delta Q? When you're dealing with a reversible process, right? Okay, so essentially this inequality, the inequality part is only talking about the irreversible process and the irreversibility of the system. Are you guys familiar with exergy analysis? Availability. Have you seen this in your thermodynamics? Okay, that's all right. Right, that's all. The irreversibility analysis is a huge part of thermodynamics. It can be a course by itself, and exergy, all of those things is actually part of those. But it is out of the scope of this course, so you don't need to worry about it. The irreversibility part ties closely with frictional losses and viscous dissipation and the appearance of shock waves in the supersonic flows. So essentially, it means that the irreversibility part is important for us in the propulsion course because we are dealing with the shock waves, we are dealing with the frictional losses, and also some viscous dissipations. Okay, any questions? So, the next step is to use the concept of entropy, the concept of Clausius inequality, and come up with some sort of an equation that helps us calculate the entropy, right? Because in the form of that inequality, right, there's no way we could use that to calculate the entropy of the system or the entropy of the two states of the system, right? So to do so, we have to go back to the work done on the system or work by the system, the elemental changes in work. And we have to keep in mind that the reversible part of work is always related to the pressure of the system. So we can find the reversible part of the work, delta W reversible, by this equation, PdV. Okay, and the viscous stress and it relates to the dissipated energy from the system, which creates that inequality and essentially the increase in entropy, right? So this equation here, delta W reversible equals to PdV, will help us to find the Gibbs equation. This is an equation that was developed by this guy named Gibbs, very important guy in thermodynamics and especially in chemical thermodynamics. And he essentially combined first and second law and came up with this equation. TdS is always equals to changes in energy, which relates to the viscous stress as the irreversible part of your system, plus your reversible work, PdV. Okay, so essentially he transformed that inequality to some sort of equality equation that we can use. He also defined enthalpy as energy of the system plus PV, pressure multiplied by the volume. Something that you have to keep in mind, I forgot to mention, is that when we are dealing with a smaller, let's say S, instead of large S, means that we are dealing with S over mass. Okay, this large S over mass. Okay. Yes. Okay. So using this definition, using this definition of enthalpy, we can rewrite the Gibbs equation. Okay. How can we do that? Very simple. Just we take the derivative of the definition of enthalpy. It's going to be dH equals to dE plus dPV. It's going to be V dP essentially plus PPV, right? the derivative of PV, because both of them are variable. We're going to use the what's that rule called? Don't remember. But it's going to be this. Okay? So you just take this. You in the Gibbs equation, you have this part and this part. So you move the VDP part to the other side, which is going to give you DH minus VDP. Okay? And you replace that in this equation. So you're going to end up with having another modified form of the Gibbs equation. TDS is going to be equal to DH minus VDP. Okay? If you take T to the other side of this equation, and use the definitions for DE and DH, which we talked about before here, you can end up with this equation. Is the link here clear? Just move T to the other side, DE and DH, CPDT, CVDT, right? Just plug them in here. You will end up with these equations, which are the main equations that are going to help you calculate the entropy or changes of entropy in a system. Okay? Between the two states of the system. So essentially, you can take the integral entropy of the second state of the system minus the entropy of the first state of the same system, delta S, changes in entropy, integral of CPDT over T minus R natural log of P2 over P1. Okay? We are using this side of the equation for that analysis, but you can also do the same analysis for this side. Which essentially is going to tell you that the integral of dt over dt, dt over t is the natural log of t at the second state, temperature at the second state over the temperature ratio, essentially, minus r multiplied by the natural log of the pressure ratios. We already have the natural log there. But you get the point. Okay? Does that make sense? Up until this? Okay. We also have just a side definition, if you will. This, the integral of CPDT from state 1 to state 2, is called the phi function. It's a specific thermodynamic function. We use this for the tabulations. You will see them in the thermodynamic tables, but you don't need it essentially. Okay. So where we want to go with all of these formulas that are listed here? We essentially want to go to gamma, to the definition of gamma and the relationship we have for gamma. We define gamma as the ratio between the pressure constant, specific heat capacity, and the volume constant heat capacity, a specific heat capacity. And that ratio, based on the equation you see here, we can see that Cp equals to Cv plus R, and Cp over R is equal to Cv over R plus 1. That's very simple, right? We have the definition of gamma. You just replace it there. Replace the definitions of Cp, the relationships we have here for the definition of gamma. You come up with this gamma equals to 1 over Cv over R. So just play with it a little bit, just mathematical play with it. You can find the definition of heat capacity based on gamma and the gas constant. Gamma over gamma minus 1 multiplied by R, and Cv is 1 over gamma minus 1 multiplied by R. Is there any questions here? No? Is it all clear? Yeah, you have seen these before, right? Yes? Okay. We can also calculate gamma. What is gamma for air? We have 1.4. That's all I want to know all of your answers. This is not right. Air, yeah. You don't remember. That's all right. Don't remember. Don't remember. Okay. That's, yeah, it is 1.4. Okay. But you are clear what gamma is, right? You have seen this before, right? Yes? Okay. We can also find gamma based on the degree of freedom of a gas molecule. What is the degree of freedom of a gas molecule? Any volunteers to answer that question? What is the degree of freedom when it comes to gas molecules?
Like the number of orientations or directions of the
That's a very good. That's a very good definition of it. It's essentially the freedom your gas molecules has to move, rotate, or vibrate, right? And also to move in relation with another molecule, right? So for the monatomic, how do you pronounce this? Gases, just single molecule, single atom gases, is going to be different. The freedom, the degree of freedom DOF is going to be different compared to the diatomic gases, right? Monatomic gas, diatomic. So we can use this formula to find the gamma for this case. And gamma is important for us because we are dealing with compressible cases. It comes into play. Also the shock, a lot of things. Gamma is a very important parameter for aerospace students in aerodynamics or aerodynamic related stuff. Okay. So if you're dealing with a single atom gas, monatomic gases, the only motions you're going to get is a translational motion in 3 spatial directions. So which means that your degree of freedom is going to be 3. Okay? So 3 plus 2, 5 over 3. Your gamma for monatomic gas is going to be at normal temperature. That's very important. It's going to be 1.667. Okay? So is air monatomic gas? How do you pronounce this word? A single atom gas. Okay, monatomic. Okay. Is air a monatomic gas? No. Why not? What is the percentage of O2? What is the percentage of O2 in air? It's around 20, right? It varies, but yeah, it's around 21, right? So if you want to simplify air, oxygen is not the best thing to choose, right? You have to choose something else.
You could add nitrogen and oxygen and get the majority of air.
That's it, right? Nitrogen 70 something percent, oxygen, but nitrogen is also N2, right? So that's a diatomic gas. So essentially, in order to find gamma for air, we have to find gamma for a diatomic gas, right? The first thing to do is to find the degrees of freedom for a diatomic gas. What is the degree of freedom? It can, of course, it moves in 3 directions, so it is already a 3. What else do we have for a diatomic gas? There is a bond between the atoms, right, and they vibrate, right? That's right. So you have the vibration. We also have a rotation, right? They are rotating around an axis. That one is usually negligible, but there are some people who claim that the degree of freedom of diatomic gases are more, but it depends. For air, we just stop at 5 essentially, right? So you're gonna get 7/5 here, which is going to give you roughly 1.4. Okay. In normal temperatures, and that normal temperature, as you can see here, it is in quotations. So why? Is there any ideas? Of course, you don't know the range of this normal temperature, but what it means is that we have a range in which the degree of freedom for monatomic gas is 3, and for diatomic gas is 5, right? For range of temperature, and outside of that range, degree of freedom is gonna change, right? Well, what is the change that comes with temperature? With higher temperatures? Lower temperatures. Why is that? Exactly. So the vibration between the two atoms is actually going to go away, right? So as you decrease the atomic gas, as you decrease the temperature, as you go to like 1 Kelvin, 2 Kelvin, like near zero absolute temperatures, you are going to get a very small vibration, and essentially your degree of freedom is going to be smaller. Okay. But what happens when you increase the temperature? When you go out of the other bond of the normal range of temperature?
You get more degrees of freedom.
Okay, why?
It's moving forward.
It's moving in more directions, right? Moving more doesn't change the degree of freedom, right? It doesn't really matter how much it's moving. The fact that it can move is already a degree of freedom, right? So moving more is not going to increase the degree of freedom, right? So what's going to happen? So the level of excitation within the atom is going to change, right? When you're dealing with higher energies. Higher temperature essentially means that higher energy for the atom, right? Essentially the electrons inside that atom is going to move to a higher level, can move to a higher level. That can be one source of a change in the degree of freedom, because that's a freedom of movement, freedom of change within the atom itself, right? So you can actually have this plot. This side of it is not n plus over n. This side is Cp over R, so you have to keep that in mind. But this side is temperature, right? As you can see, we have a region for air between 3 Kelvin, very small, and 600 Kelvin. Then we can safely assume that your gamma is constant, right? 1.4. But afterwards, when you increase the temperature, your gamma is going to change. And actually, gamma is going to decrease, but this is Cp over R. So again, so higher degrees of freedom, lower gamma. Okay. Any questions so far? What time is it? I don't want to go. Our class is supposed to run till 11:40, right? Okay. Let's move to the isentropic processes. What is an isentropic process? Reversible and adiabatic, right? So isentropic process, we can rewrite the relationship between the temperature, pressure, and also the density for a calorically perfect gas. What was a calorically perfect gas? When Cp and Cp are not a function of temperature, right? Or constant, as far as temperature is constant. So using those, you can come up with these equations for the pressure ratio between the two states. P2 over P1 is equal to P2 over T1 to the power Cp over R, which is equal to, we know that Cp over R is gamma over gamma minus 1. Okay, so T2 over T1 is going to be equal to T2 over T1 to the power gamma over gamma minus 1. And you can actually use the ideal gas law to rewrite this equation and come with the relationship between pressure ratio and the density ratios. P2 over P1 is equal to rho 2 over rho 1 to the power of gamma. Any questions? Isentropic relations are of somewhat importance in propulsion course, but we'll get to that part later in the semester. So let's get to the conservation principles. The conservation concept, we have two main conservation here. It is correct here, right? It is not conversation. We have two main conservation principles. It doesn't matter where you are in thermal fluid analysis, these three main conservation principles are there. Going to be the governing equations for the movement of the fluid, essentially. Whatever kind of fluid you have. The conservation of mass, which tells you that the changes of mass inside the control volume over time is equals to the difference between the mass coming in, the mass flow rate coming in, and the mass flow rate going back. Okay? And the momentum equation, which is a directional equation, and relates force and moment together, says essentially a force balance equation, if you will. And I said balance. It's the balance of forces within a control volume, or the momentum equation tells you that whatever changes in momentum you have inside a control volume. Right? Do you guys know what a control volume is? Just assume you all know what a control volume is. Yes? Okay. So whatever change of momentum you have inside a control volume over time, right? The rate of change of momentum over time is going to be equal to the total of forces that is being applied to it. Mostly in the fluid case, it's just weight, right? But in propulsion case, we don't have that weight as well. Air is assumed to be weightless. And the changes of momentum on the surfaces of that control volume. So it's essentially the fluxes coming in, the fluxes of force coming in as well. Okay? Which we can simplify to this for our specific case. We are assuming uniform flow, everything, a lot of assumptions have been made to get from here to here. Okay. So m dot v out minus m dot v in equals to the total of forces. Here we are assuming a single inlet, a single outlet, right? We are assuming uniform flow, so we could do the integrations without any problem. And so on and so forth. The conservation of energy part, the same thing, the changes of energy inside the system, generation, whatever you have, changes of energy, the fluxes of energy at the surfaces, equals to the shaft power, the viscous dissipation, the rate of heat generation within the system. Okay. You should have seen these two if you have taken your fluid mechanics or aerodynamics. If you have not, that's all right. Hopefully, whenever we need them, we'll go into more detail, so you guys will have a better understanding. And if you have taken heat transfer, which most of you said you have, right? You have not. What about you? Have you taken heat transfer?
No.
What about fluid mechanics? Oh, you are an aerospace student. You are not mechanical, right?
No,
Aerospace. Have you taken aerodynamics?
Oh, yeah.
Okay. So you have seen these three then?
Oh, yeah.
Yeah. Okay. Yeah. Conservation of energy. Then you have seen in either heat transfer or aerodynamics, or yeah. If you make the uniform flow assumption, we can reduce the conservation of energy to this shaft power, the changes of heat within your system, the generation or heat loss within the system, and whatever energy coming in minus whatever energy going out minus whatever energy coming in. And keep in mind that this H of T is not your regular enthalpy, it's total enthalpy. And we'll talk about the total conditions in a little bit. If there is no shaft work and if your system is adiabatic, your energy must be conserved, right? That's the idea. So whatever the total enthalpy of the exit must be equal to the total enthalpy of the inlet. Okay. We're a little behind. Okay, let's talk about sound waves. Sound waves and the speed of sound. So essentially the idea is sound waves are infinitesimal pressure waves that propagate through a medium. The main assumption we make as far as the sound waves go is that they are reversible and adiabatic, so essentially isentropic. And based on these two main assumptions and definitions, we can safely say that the sound waves are essentially the collision of the fluid molecules. So if the fluid molecules are closer to each other, they're going to collide with each other faster, right? So the sound can travel faster in liquids or in denser fluids, or in liquids faster than gases. Okay. And I wanted to go through the proof of equation for the speed of sound. I think I have enough time. So essentially, if you write that, let's say you have two states before and after a sound wave that is moving with a speed, right? If you simplify the continuity equation or the conservation of mass equation, this is what you're going to get. Rho u is going to be the rho plus the changes of density multiplied by the velocity plus the changes of velocity. That's after and before the sound wave, right? And you can simplify this. You can just multiply these together. You can simplify this to get to this equation. Rho du is equals to negative u d rho, right? If you do the same thing for the momentum equation, this is what you're going to get. Do the simplification. Rho u multiplied by u plus du minus rho u multiplied by u is equals to P minus P plus dP. Essentially, your delta P changes in temperature and in the pressure. Very easy to simplify. If you simplify it, this is what you're going to get. Rho u du is equals to dP. Okay, any questions so far? Okay, we can simply, there is a very small mistake here. So this should be negative dP. Okay, so taking a note, this should be negative dP. But you can use the conservation of mass equation for this case, plug it in here, and get to this equation. U squared dP, d rho is equals to dP. And the main assumption we had was that this is an isentropic process, so entropy constant. U squared is equals to dP over d rho, or partial P over partial rho, where entropy is constant. And we have the equation for partial P over partial rho. And just use gamma P over gamma rho. U squared can be equal to that. And based on the ideal gas law, P over rho is equals to RT. So U squared is going to be gamma RT, right? And this is the speed of that sound wave if we use A, right? So A speed of sound can be calculated by the square root of gamma P over rho, or the square root of gamma RT. We can actually play with it a little bit and come up with another equation, gamma minus 1 Cp multiplied by T. So whatever you have, you can just use, if you have the Cp, you can use the third equation. If you have R, you can use the second, and so on and so forth to find the speed of sound, okay? So the thing we use, 11:15. So the thing we use in aerodynamics, and keep in mind that propulsion is essentially internal aerodynamics, right? If you have taken the aerodynamics course, then whatever you deal with, you're dealing with external flow, a flow on a wing, right? That's an external flow. But in propulsion, we are dealing with internal aerodynamics or internal fluid mechanics of air, right? So in propulsion, we need to deal with Mach number. Same is true for aerodynamics, right? We have subsonic flows, supersonic flows, transonic flows. Right? We have the sonic conditions, and we have to understand the difference between the subsonic flows and supersonic flows. So what are the subsonic and supersonic? Sonic condition essentially means that moving at the speed of sound. Okay, if you are moving at higher than the speed of sound, you're in the supersonic conditions. If you're moving at the lower speed of sound, lower than the speed of sound, you are moving at the subsonic condition. Okay, so but then the question is, what is the main difference between the supersonic condition and the subsonic condition? That's the question I want to pose to you guys. I want to pose it to the new guys in class. I mean, like the people I didn't know before. All of you are new in class. So it's Nick, Matt, right? Matt, Lorianne, and what was the name? Nirlev, right? So I pronounced it correctly in the first one. Nirlev, okay. So one of you guys, tell me what's the main difference between, you guys understand the supersonic and subsonic, right? Okay, what is the main difference between supersonic and subsonic flows?
Supersonic, their shock waves generated.
There is, exactly. So that's the main difference is going to be the generation of shock waves. And shock waves are essentially very thin layers after which there is essentially, you can say that there is a separation inside the flow, right? A separation happens, a discontinuity happens, right? Yeah, very like high pressure, low pressure behind or after the shock waves. So we essentially have a discontinuity. But the thing we want to discuss here is that why do we have the shock waves when we are in the supersonic condition, right? Is there anyone who can answer that question? Let's say we are dealing with a beeper. That's a very famous example whenever you want to talk about shock waves, right?
There's some pressure separation along the wings on an aircraft.
Pressure, okay.
Like there's some air that flows over the wing, and the faster it goes, the more it separates from the top and the bottom.
Yeah, are you talking about the flow separation at the tail?
Yeah, flow separation.
That is not the reason behind the shock wave, no. Okay, anyone else? From the, yeah, I mean, you guys know the reason because you should know the reason. You have been in the class with me. I've taught to you, right? So if you don't, then.
Does that have to do with the Doppler effect?
Doppler effect. You're very, very warm. I don't know, but I don't know how you want to connect the Doppler effect to this.
It's just like where
You were saying, you were continuing?
like the air in front can't keep up with the air moving back. So like, it's just like I don't know how to put it in words.
I mean, yeah,
Once you pass that certain point, the air in the front kind of just.
I think you're moving in the right direction. Okay. Okay. Do you want to add something?
You have it illustrated there, so that's like right where it's about to break into supersonic.
Don't worry about this. I don't think you. I don't think you can explain this with these illustrations. But do you guys You have the philosopher's thing. Do you have anything to add? Okay. So, do you guys want to explain? Any of you guys? No?
Does it have anything so breaking of the sound barrier is associated with the shock wave?
Essentially, it is you are moving out higher than the supersonic conditions, right? So the waves you are sending are more energetic than the sound waves, right? That's the idea. You didn't want to add anything? Okay. Do you want to?
Well, essentially, like, as you're moving through the air, the sound waves are propagating in front of you, but as you approach speed of sound, the waves they can no longer travel in front of you, and they all start to pile up.
Okay, exactly. So it is a very simple concept, as Brian mentioned. Let's say you have a beeper, okay, that is moving at a speed lower than the speed of sound. Okay? So essentially subsonic conditions, regular flight, right? And it's beeping, right? So the beeper is generating sound waves. As it moves, the sound waves are propagating are always ahead of this beeper itself, right? Because it is moving at a slower speed compared to the speed of sound. Does that make sense? So it doesn't matter when the beep was generated. If it was generated like a while ago or just right now, that beep is always ahead of the beeper. Does that make sense? Because the beeper is moving at a speed slower than the speed of sound, right? But what's going to happen when your beeper is going faster than the speed of sound? What's going to happen? So at some point, let's say this is the first, let's go back to the start of the movement. Let's say this is the time 0. I'm going to say 0 plus, just a little after the initial condition, right? And you already have a beep generated, so you will have a sound wave propagating through the space, but you haven't moved that much yet. Okay? Let's say we are progressing in time, and this is a time progress, right? That initial sound wave has moved some distance, right? Let's say this was your initial. So this is time 0, this is time t1, right? This is your initial part in a space, point in a space, x1, x2, right? And here you're talking about x1, okay? So that initial sound wave that was generated here has moved, right? Has propagated through space. But it has propagated through space at a slower pace than the beeper itself. So the beeper is actually already outside the initial sound wave. Does that make sense? Yes? Okay. So let's say you have had this sound wave, the initial one, then when beeper was here, it has generated another sound wave, another sound wave, another sound wave. And as we said, sound waves are essentially pressure waves, right? So the pressure before or behind and in front of a sound wave is going to be different, right? But here you will have a cultivation of millions of sound waves, right? They are just packed together, which means that the pressure behind and in front of the shock wave is going to be very different because you have like millions of these sound waves packed together. Does that make sense? So this is your shock wave. This is the shock wave. That's it. And it is there because your beeper is moving. Yeah, that is correct. It's moving at a higher speed than the speed of light. We can actually calculate the Mach angle. This is called the Mach angle. Right? The angle that the shock wave makes with your path of movement. The Mach angle can be calculated using this formula. The inverse sine of the speed of sound multiplied by time that has passed from the beginning of your movement, over the velocity of your beeper multiplied by time, which is equals to the inverse sine of 1 over m. Okay. Is there any questions?
Do you can like visually change each mock you go, or is it the same? Like it's just more.
What do you mean by visually change?
Like I didn't know if there was like some change with the mock weight.
As long as you are higher than Mach, let's say Mach 1.2, okay? Because Mach, let's say Mach 1. Let's just stick to the official narrative, right? You will see the shock wave, for shock waves generation, right? As you move fast, what's going to happen when you move faster? No, these people should answer. Huh? That's all right. They're at the end of the class. I don't have to push it. But the angle may change a little bit, right? But that's it. The visualization is just a discontinuity in your system. That's it. That's it. Okay, so let's talk about the class a little bit. Hopefully we have had a good recording.